Multi-qubit gates are of two types, like your 2-qubit and 3-qubit gates. So your 2-qubit gates include C0, swap, controlled U gate, and your C swap gate. So swap and C swap are one and the same, just another control bit line we are adding. You will see it later on. And your 3-qubit gate is your Toffoli gate. This is also known as your C0 and CCX. These are some another name for Toffoli. This is your 3-qubit gate. So let's start with your C0 first. So this is your control line and this is your target line. And your control line is get, suppose, no, not this one, sorry. Yeah, I'll take the example later on. For now, just understand this is your control line, this is your target line. Okay, so first qubit, this is your first qubit, which is your control line, and your second qubit is your target line. So when we are representing it is like 0 0. Okay, so this is your control and this is your target. This is how we represent CC0. For the single qubit we were using only one qubit. This is multi-qubit, so we are using more than one. So since we are learning 2 qubits, so for all these gates, when we'll represent it, we'll be using, for input we'll be giving 2 qubits as an input, like we have given for CC0. Okay, now let's look into the truth table of the same. Your input, your output. Okay, now input is like, okay, so for the output, now one thing you should remember about your C0 gate is that when your control bit, okay, when your control bit is 0, there would be no changes, and when your control bit is 1, the target is flipped. So like here, when your control bit is 0, let me change the color. Yeah, so your control bit is 0, your control bit is 0, so here we don't have to make any changes. Your control bit is 0, no changes required. Here control bit is 1, here control bit is 1, so what I told is target would be swapped. So write this control bit as it is, and this target would be swapped. 0 from 0 it will become 1, and from 1 it becomes 0. So this is how our truth table would look like for CC0. Using the truth table, again we can write the direct notation and solve. Okay, but here you will ask for 2-qubit gate. The representation I gave you before for cat not, cat 0, bra 0, cat 1 and bra 1. Okay, for those, this like this 1 0, like this. Okay, like this matrix what I told you in before lecture. So for this, here we are having 2 qubits, correct, for 0 and 0. So you can't write same for this. So how to calculate for this? Just once you calculate, you'll remember it. No need to calculate again and again every time you write. Okay, so once you calculate, just show one calculation when you write the answer in the paper, or when you derive in the paper. Just write for one derivation, and rest all it is understandable, correct. So for 0 0, how we can write this it as ket 0 tensor product of ket 0, ket 0 and ket 0, when we are doing tensor product. Okay, so like how we are representing ket 0, this we know, 1 0. Again, how we are representing ket 0, this we know, 1 0. Okay, so what we will do here is multiplication normal. Okay, this and this. So 1 into 1 is your 1, 1 into 0 0, 0 into 0 0, 0 into 0 0. So this is how your matrix would look like for ket 0 0. And for all the four possible combination, let me write the matrix. Yeah, this is how your representation of this 2 qubits would look like in matrix format. So what we have to do is just substitute these matrices instead of this input, and we'll derive the matrix. So a direct notation for this C naught would look like C naught. Okay. So here instead of 0 0, just substitute 1 0 0 0, and here 1 0 0 0, and similarly dot 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 I'm doing for all. Okay, for all just do the same thing, and then you multiply these matrix 1 into 1 1 into 0, and resultant what you will get is 4 by 4 matrix for each one. Okay, so we'll be getting 1, all zeros, 1 2 3. So this is how this first one for this is how it would look like. For all these you just calculate. Okay, and later on the final matrix how it will look like is for C naught. Yeah, here is the representation. So this is all about your C naught gate. Okay, your C naught gate, this is your truth table for your C naught gate. Okay, this is your truth table, and this is the representation how we represent the C naught gate, and this is your direct notation, and this is the matrix. And derivation, as I told you, you can do it, and it is given in my notes as well. And this is something you need to remember for 2 qubit gate or multi-qubit gates. Okay, and suppose if we here it is 2 qubits, suppose if we have 3 qubits, then do this similar thing what we are doing here, tensor product. Suppose it becomes 0 0 0, now you have 0 0 0. Okay, so for this what you will do, 0 tensor product get 0, tensor product of get 0. Okay, so this is how it look like. So when you result, like when you calculate this matrix would come like this: 1 and then 1 2 3 4 5 6 7. So 8 terms would be there, and all 0, first one would be 1 for triple 0. Okay, and likewise 8 different values you will get. So I'll just brief about the other multi-qubit gates. The derivation and everything is given in the notes, and they are pretty much easy and the same as we have done for the above one. Okay, so like swap, this is like kind of swapping the two control bits, not control, but 2 bits, 2 qubits we are swapping. So when the two are same, both of the qubits are same, keep it similar. When both are same, keep it as it is. When 0 1, when both qubits are different, swap them. When both qubits are different, swap them. Okay, let me change the color little bit. Okay, so like here these are the two conditions. When they are different, you have to swap. So this is the basic what is our swap gate looks like. So controlled u is like here you are having a controlled u line. Okay, where this is your control, and the target you are having this u line. So there you can control or replace u with your x gate, your y gate, or your z gate. Whatever you need, you can replace this u with x, y, or z gate or poly gates, and that becomes your controlled u gate. So yeah, the truth table, you no need to learn the truth table for this, like just understand what it is. That's why I have given. Okay, so like the C swap, or what we C stand for your control, and swap. So here what how we see, we have seen before your control gate. What is your control gate? So like there's a control line and there's a target line. Whenever your control line becomes 1, the target is flipped. Okay, and your swap is like whenever the both qubits are different, then we swap them. So this is your combination of those two gate, that is control swap gate. This is your 3 qubit gate. So like this, your first qubit is your control qubit or control line, and the other two are your target lines. Okay, so if your first qubit is 1, when your first qubit is 1, your control is 1, only then the swapping of these target qubits will take place, else everything would remain as it is. So here, since these are 3 qubit gate, it is represented as 000, 001, like these would be the inputs, okay, 0, and so on. So like this you will get 8. So among those 8, only that will change where your control bit is 1, that is the 4, where your first bit is 1, that is 1000, 101, 110, sorry, 111. For all those 4 combinations, what you'll have to do is you have to swap your target bits. Okay, this is how your control swap looks like. And C naught, or TOEFL, the controlled C naught gate. Okay, so here we have two control line. In C swap we have two target line and one control. In C naught we have two control line. Control is done using two control lines and only one target line. Okay, so flip target qubit if both control are 1, like if both the controls are 1, okay, then only the target will be flipped, else it will be remain as it is. So again here you will get this 3 qubit 8 combinations of input. So from those input, only two input which will have your input as 110 and 111, only these input, the target bit will be swapped, that is it would become 111 and 110. Okay, so that is all about C naught or TOEFL, and this is all about quantum qubit gates. We have learned single qubit, we have learned multi qubit, and we have seen the derivation for almost every, like whatever I have given all the derivations in the description in notes. Again and again I'm telling, just go and refer to that. Once you read it, you no need to solve also. Once you just read it, you'll understand each and every single point, and like it is way too easy. Thank you.